Okay, in this lecture we're going to discuss the Laplace transform. This is part of the unit on transforms, but it also overlaps with our unit on ordinary differential equations because one of the applications of the Laplace transform is the solution of ordinary differential equations. Now, much of this lecture will be repeated in our class meeting, so this is here just primarily for purposes of for you to have a reference of what we're doing in Laplace transforms. And a backup set of video notes so that you can watch if there was any point of confusion. This lecture will not contain a great number of example problems, which in my opinion is one of the best ways to learn about the Laplace transform. So mostly some somewhat theoretical math speak from your textbook is what we'll have here. And then example problems and related information we'll go over in class. So in the Laplace transform, primarily the Laplace transform is applicable to initial value problems. So when you have a physical system where you have some initial value and you have a differential equation that describes the physical system, then you can basically take that initial value problem and using the transform, you can transform that from a differential equation to an algebraic equation. You can then solve the algebraic equation by using basic algebra and then take the inverse transform to obtain the solution to the initial value problem. So this is just a schematic that illustrates that. So in step one, we transform the differential equation into an algebraic equation. In your textbook, that's referred to as the subsidiary equation. The subsidiary equation is solved, and then the result is transformed back, giving the problem solution. So the main motivation is that the process of solving a differential equation is much easier. And there are two main advantages that we see. The first is problems are solved more directly. So you don't have to first determine a general solution to solve an initial value problem because, as you'll see, that's going to be built in to the solution when we take the Laplace transform. And also, inhomogeneous differential equations can be solved without first solving the homogeneous differential equation. So it's basically a one-step process. More significantly, the fact that the unit step function and the direct delta function are very commonly used and have very basic and simple Laplace transforms. This means that if we have problems that have inputs with discontinuities or short impulses or complicated periodic functions, they're much easier to solve using the Laplace transform methods. So in electrical engineering, to use a couple of concrete examples, problems that involve initial conditions on capacitors or inductors, for example, are often solved using the Laplace transform because we have a clearly defined point at which we define t equals 0. There's usually a switch that applies a voltage or switches a charged capacitor. And so that then gives us these initial value problems. And we can use the unit step, as you probably learned in a circuits class, to model those kinds of systems. On the other hand, if we have complicated signals with multiple frequency content that are more or less continuous from negative infinity to infinity, the Laplace transform is probably not the best approach to model that kind of problem. That's probably better modeled with the Fourier transform. So there are clear applications for both kinds of transforms in electrical engineering. So there are a couple of important definitions and theorems regarding the Laplace transform. First of all, just basically where is the Laplace transform defined? And once again, we are discussing the single-sided transform. So our integral in the transform is going to run from 0 to infinity. F of t is our function of time. And we have to assume that f of t is the kind of function that will have an integral that exists from 0 to infinity. Most of the time, that property is satisfied. The L here, and when I work with Laplace transforms in class, I always use a script L, and a lot of electrical engineering textbooks will use a script L as well. Indicates that we're taking the Laplace transform, and then notice that when we've completed the transform, the lowercase functional symbol goes to uppercase, and the t has been integrated away, and now our transform variable is s. S is known as a complex frequency. It has a real part and an imaginary part, but it's not the kind of thing where we separate out the real part and the imaginary part, only in very special applications. So this is a basic integral transform, similar to the integral transform we defined in the previous lecture. So here's your kernel function k, and in this case the kernel function for the Laplace transform is e to the minus st. It involves a process of integration and a kernel, so it's referred to as an integral transform. The inverse transform is defined using terminology of L minus 1, indicates taking the inverse transform of the function in complex frequency space, and out of that we will get a time domain function. It's not a symmetric transform. However, if we take the inverse transform of the transform, we should get the function back. Some notation, as we mentioned, the capital letter as a function of s denotes the transform of a lowercase letter function of t, and so on. And that's fairly consistent across the textbooks. The Laplace transform is linear. So if we have a function that is f of t and a g of t, first of all, if they're multiplied by a constant, the constant can be pulled out of the transform process. So just like if it were just normal integration, which basically it is, you could pull a constant out of the integral. If we have a sum of two functions, then the transform of the sum is the sum of the transforms, which is essentially the definition of linearity. And since this is effectively an integral process, it is in fact a linear process. Here are some tables that indicate functions of time and the Laplace transform of that function. This is assuming single-sided transforms. So if we have a constant, the transform goes to 1 over s. If we have linear t, the transform goes to 1 over s squared, and so on. And then that pattern repeats. So if we have t to the power n, then the transform is n factorial over s to the n plus 1. E to the at, which is a fairly common one, transforms into 1 over s minus a. Sine, cosine, hyperbolic cosine and sine, and exponentially damped sine and cosine are all given here. As a general rule, a in electrical engineering, this little constant in the exponential a is typically a negative number, making for a stable system. If in electrical engineering a is a positive number, we typically have instability and exponential growth, and that's not sustainable in a physical problem. So if you are working a problem and you get something like 1 over s minus 3, you know that you've probably made an error, because you should be looking at terms that look like 1 over s plus 3. Now, how you get this table, and we'll do a little bit of this live in some of the example lectures. How you get this table is you get this table from taking f of t, plugging it into the integral transform function, completing the integration, and what you get out is what's found in the transform column. So a common theorem is called S-shifting, and this is fairly common. This happens when you have a function of time that is multiplied by e to the s, e to the at. When you do that, there is a predictable output, and that is the Laplace transform of a function of time that's multiplied by that exponential. Basically, what this means, this f of s minus a, it means you would take your f of t and you would take the normal transform where you get f of s. And then this e to the at part, what it effectively does is everywhere you have an s in your transform, you would substitute with s minus a. So that becomes an extremely valuable thing both in taking the transform and the inverse transform, because in taking the inverse transform, if you can get your function in the s domain to look like s minus a, then sometimes it's much simpler to take the inverse transform from a table and then just modulate that with this e to the at. So this is a very important theorem that shows up a lot in Laplace transforms. Okay, we're going to conclude that lecture here, and then the next lecture we will talk about transforms of derivatives and integrals.